Uh, Good morning to everyone in Binghamton, and good evening, everybody from VIT Shine. So today, this is the third seminar series with the VIT Shine and the SSI at Binghamton University. Today we have Dr. Yingge Zhou, who will be presenting a topic on fabrication of vascularized scaffolds for tissue engineering. Dr. Yingge Zhou received his PhD from the Department of Industrial Manufacturing and Systems Engineering at Texas Tech University. He also earned his master's degree there from Texas Tech. He also have a bachelor's in mechanical engineering and business administration at Xiangtang University in China. His current research focuses on microfabrication and hybrid manufacturing of 3D biomimetic architecture in hybrid bioprinting systems. His most recent work focused on sacrificial 3D printing, tissue scaffolds templates, and electrospray microparticles for drug delivery applications. His teaching interests include manufacturing systems, additive manufacturing, medical design, and manufacturing. He's also a member of IISc and ASME, and we are very happy to have Dr. Yingge Zhou in today's talk. Dr. Zhou, yeah, please.
Okay, thank you, Dr. Serena Smithfield. So, good morning from Binghamton, and good evening to everyone in VIT Shine, including the professors and students. Thank you for the opportunity, and thank you for joining this seminar. So, again, I'll skip my self-introduction as Serena's just introduced me. So, I'm an assistant professor, joined in the department in 2020 in the middle of the COVID. My research focus on the advanced manufacturing, additive manufacturing, and biomedical manufacturing. So basically, it's all of the manufacturing applications, processes, and mechanisms. Today, I'll introduce three of my research projects, and they're all related to the fabrication of vascularized scaffolds for tissue engineering. So without further ado, I'll start the presentation. So the first project will be about the biomimicry of capillary scaffolds using the electrospinning technique to fabricate the tubular structure with micron scale. And the second topic was about use the 3D printing to as a kind of a sacrificial template for the hydrogel to mold to tissue scaffolds. And in this case, how does it compare with the directly bioprint the hydrogel? And the third one is the use electrospray technique to make the core shell microparticle carrier for drug deliveries for lung diseases. This is a collaboration project with Upstate Medical University in our State University of New York system in Syracuse. So I'll start with the first project. So please feel free to stop me or interrupt me anytime for any questions. So a little bit of the background, what is tissue engineering and why it's needed. The first one is people always have organ failure when they're getting old or when they have any diseases. So usually we just transplant the organ from somebody else, or we develop an animal model and transfer from the animal. However, as you can see in the figure below, there's always more people on the waiting list compared to the people who is giving organ, needing an organ and giving organs. And if you're transplanting from someone else, usually your immune system will attack it after a certain amount of time. So there's a body rejection issue. And also, if you're transplanting from the animal models, then you could face moral conflicts, not to mention body rejections as well. So tissue engineering emerges in the last couple of decades as a interdisciplinary field to improve or replace tissues or organs with engineering methods. So by engineering methods, we're inferring to developing the tissue or organ using the patient's own cells. So its global market size is projected to be 48 billion by 2032. So what the process is, we get the cells from the patient, and then we expand the cells. We try to differentiate the cells into stem cells, and then develop them into different cells. So how do we develop into different type of cells? First, we need the physical scaffold for the cells to be attached to, and the scaffold has to be biodegradable, biocompatible, and biomimetic, which means they have to disappear after cells are formed to a certain type of preliminary organ shape. And they have to be biocompatible, which means they cannot do damage to cells. They cannot be toxic to cells. And they cannot secrete or produce any harmful materials over time when they degrade. And the third one, most importantly related to engineer or manufacturing, is we have to make the shape, the morphology, the mechanical strengths, and other chemical and physical properties very similar to our native tissues and organs. Otherwise, the cells won't be guided to a certain type of cells or preliminary organ formation in that case. So that's the engineering methods that we're focusing on as the industrial engineer, the 3D manufacturing of 3D scaffolds. And then after we get the scaffolds, we kind of pass it along to biomedical engineers. They put cells in it, they put the biological factors, including growth factors, chemical factors, and other factors into it. Then hopefully in the future, we'll be able to develop some preliminary type of tissues and organs. We already have a very few examples for tissues and organs developed. For example, liver, which liver is a comparatively simple structure compared to other organs. So I would say it's possible, but it's still developing. So the research gap for the first project is we have the scaffolds, but we don't have the vessels. So in order to build vessels, you need to build hollow structures within scaffolds. For example, we in the human body, we have artery, we have vein, we have capillaries. For arteries and veins, they are kind of a macro scale, then in millimeter or even centimeter scale. So it's possible for us to use bioprinters to print them. But for the capillaries, which are from 1 to 10 microns, it's really hard given the current bioprinters resolution, especially material limitation. Usually we use hydrogel to print the scaffolds. So you can imagine it's really hard to create 1 to 10 micron tubes or channels within the hydrogel scaffolds just by using bioprinting. And also, there are some surface pores on the capillaries in our human body, which means the surface pores will be in nano size, not the micro size. So it's even harder for the bioprinter to create the surface pores. And also, the third gap is the 3D structure of the capillaries within human body, as you can see in the figure below. This is bone and this is liver. The 3D structure for the capillary vessels is really complicated, right? So it's really hard to 3D model it or 3D print it. We can only probably mimic it using certain type of techniques. So for capillary vessels, we probably need another solution. And the manufacturing process we're exploring is the electrospinning. Electrospinning is a process that uses the high voltage to generate fibers, particles, or tubes based on your setup. And we have the micro pumps that's going to pump the different polymer solutions out of the needles. And on the needle tip, we have a high voltage. The voltage amount we're talking about is about 10,000 watts, 10,000 watts. And then the high voltage will help the needle tip, the solution in the needle tip, to break surface tension of the polymer, which is the electrical force will exceed the surface tension of the polymer. When the electric force exceeds the surface tension of the polymer, there will be a jet coming out of the needle tip. When the jet is coming out and the electric force is still in effect, the jet will accelerate and form a fiber structure before it goes to the bottom collectors. So the collector has to be conductive and grounded as well to be able to collect the structure. And here we use the customized collector. As you can see, we have two bars. These two bars are metal bars, which means they're conductive. And we put these two bars symmetrically below the syringe. Therefore, we will collect fibers between these two bars, and they're parallel fibers, mostly parallel fibers. And the material we use is POA and PO. They are both biocompatible polymers, which PLA is not dissolvable in water and PO is dissolvable in water. So we can dissolve PO in water and PLA in another organic solvent and then put them in this kind of a core shell manner of the syringe. And then when they extrude out, the syringe will have a core shell fibers. And because the core is dissolvable in the water, then after we collect the fibers, we put this whole sample into water for water immersion to dissolve the core. Therefore, we got the tubes instead of the fibers. We got the tubes. Okay, now we have to demonstrate we got the tubes. That's the most difficult part that we met because the polymer is really soft. The polymer is really soft. You can stretch it, but you cannot break it down. If you use a scissor to cut it, the opening will be closed. But we want to get a microscope image. So we put the collected microtube sample, which is in a matte format, matte form, into a sandwich structure clamped by ice. And then we break this ice in the minus 80 degree freezer. Minus 80 Celsius degree freezer. We'll break it. When we break it, and then the ice will be melted because in the SEM you cannot have any moisture or water content. And then we got the cross section of the mat. Then we proved that we got tubes instead of fibers, and those tubes are really nice tubes, as you can see in the SEM. So our next step is to investigate how can we use the electrospinning parameter to control, for example, the diameter and the wall thickness of the tubes. And we can also see there's some surface pores on the tubes. So for the diameter range from 5 to 12 microns, even though it's not 1 to 10 microns compared to our native human capillary vessels, but it's pretty close. It's usable. We can also fine-tune it to make it a little bit smaller. So the electrospinning parameters we're investigating here is the tip to base distance, which is the distance between the collector and the syringe in the electrospinning setup, and also the pump ratio. The pump ratio is the material ratio between the core material and the shell material, which is PLA and PO. Now we will want to see if these two things will have effect on the microtube diameter, and it shows that both these two factors have significant effects, statistically important, P smaller than 0.05, significantly effect on the microtube diameter. And the next one is wall thickness. You can see in the SEM image here, the wall thickness range from 0.5 to 2.5 microns. Why the wall thickness matters is because we want to know if the surface pores are they just surface or are they through holes? If the wall thickness is too thick, then the surface pores will not be able to penetrate into the microtube, and therefore it cannot function as capillary vessels. So we want to see if you can control the wall thickness as well. And then we found out that only the pump ratio has the significant effect on the wall thickness. The distance has no significant effect to the wall thickness. We also investigate the pore size, but due to the time limit, I'll skip it here because I still have 2 more projects to cover. So we put the cells into the microtube scaffold, and this is a microtube only, and this is the cells in the microtube. This is cell nucleus and this cell cytoplasm. After a couple of days, we find out the cells still happy, so which means they're not toxic. And what's next is we break down these microtubes using ultrasonic vibration, and then incorporate them into the bioprinting hydrogel. So we have different lengths of the microtubes. For example, based on this ultrasonic sonication time, you can have average 600 micrometer length of microtubes. You can also have just maybe 50 micrometer microtube length. And then we blend them into the bioprinting hydrogel and bioprint the filament to try if the microtube is long, if the microtube is short, if the microtube concentration in the hydrogel is high, which is 0.01, it's pretty high already based on our test, and if it's low, which is 0.05%. And then we test the alignment of microtubes within the hydrogel when we print it out. We want to see if the hydrogel microtube in the hydrogel has some alignments. And it looks like they do have some alignment, not very uniform, but they do have some alignment. No matter it's long or short, no matter if it's high or low percentage concentration. Of course, the short one with high concentration has lower alignment. And then we culture some cells with blood vessel cells, which is endothelial cells. And put it into the blood vessel cells, and this is a microfluidic device. We created some microfluidic flow of the culture medium, and to see if they are going to form some kind of preliminary vessel openings or structures. It looks like the perfusible structures and openings with microtube are more compared to without microtubes, which means microtube helped the formation of the vessel openings or lumens. When we test with the fluorescent microparticles, they can pass from the left side to the right side of this microfluidic device. And we also test the viability, see if the hydrogel with the microtube is harmful to the cells. And it looks like with microtube, is not harmful. It's still above 80% compared to control with cell only. Yeah. So this is the first project. Any question, feel free to raise up. And the second project will be the 3D printing assisted hydrogel molding. So the problem with bioprinting hydrogel is we don't have enough simulated vessels. So we can incorporate microtubes into the bioprinted vessels, right? But what about the macrotubes? What about if the microtube, we want to control the size and geometry, right? So when we incorporate in the first project, when we incorporate the microtubes in the hydrogel, we cannot control how the microtube is going to align. So how can we directly control it? This is a research gap. And then we developed a 3D printing structure to just print the vessel or the channel structure. Here is a simple channel structure. This is 3D model, and then we try to stack them together, and then we print it using SLA printer. SLA has pretty high resolution. We can also print it with FDM, as long as the material is dissolvable in water. Then we create a mold, and then pull the hydrogel into the mold, and then let the hydrogel cross-link, and then dissolve the mold in the water. Then the hydrogel, after cross-link, is going to form some channels within the hydrogel. And this channel, the shape and geometry and the resolution, we can control it. And also, we are pulling the hydrogel into this mold. We're not extruding the hydrogel from the bioprinter nozzle, which means the damage to the cells will be minimized. So this is another advantage. We want to have heat and stress-free for cells. And the resolution of the hydrogel is dependent on the printer, no longer on the hydrogel materials limitation. So we test out the different structures, for example, 2x2 channel, 4x4 channel, 6x6 channel, and the channel size 400 micron, 800 micron, 1600 micron. And turns out they are really high resolution and really perfusible, and they're interconnected. When we put dye from one angle, the dye is going to penetrate through all the scaffold. And we also tested the size of the hydrogel, of the channel within the hydrogel, because hydrogel is soft. So if the channel is too big, then the channel will be deformed. And this is also what we found. The 1600 micron has more deformation, and the 6x6 bars also has more deformation. The larger the size, the higher the deformation. And the smaller the size, the lower the standard deviation of the diameter and the circularity. And then we try to see if we can control the material release within the hydrogel to the culture medium, or from the culture medium to the hydrogel, because now we have channels, right? So what does it look like if the hydrogel has no channels, and the dye in the hydrogel is going to release into the medium? How fast it's going to be? If no hydrogel, the release rate is pretty low, only about 30% in 18 hours. But with hydrogel, it's pretty high. And the highest is 6x6 channels and the 1600 micron channels. So the larger the channels, the more channels, the better or the faster the release, which is reasonable, right? And this lower one is the 2x2 and 400, as you can see. So this is the drug release. We want to see if we can control the drug or biological release profile. And then the next one is a degradability. Because you remember the hydrogel is a scaffold. They have to be degradable. Can we control the degradability with the cells, with channels in the cell scaffold? And we take a look and see that the hydrogel with channels will have higher degradability. And they're going to reach the same amount of degradability and at the day 14, but the one with channels will release better. And we also want to see if they're toxic. For example, we 3D printed something, even though we dissolved it, it leaves some residual in the scaffold that make it toxic to the cells. It looks like after 24 hours, 48 hours, and 72 hours, the cell will be still above 75%. Yeah. And then we culture some cells. We incorporate the cells with the hydrogel when we pour the hydrogel into the mold. We take a look at day 0, with and without channels. At day 0, the cell's still living. The green one means living cells. The red one means dead cells. At day 7, if the hydrogel has no channel, almost every cell dead. Not really happy. And then if the hydrogel has a channel, then the cell availability in the center of the hydrogel is pretty high, because in the surface of hydrogel, they can contact with the cell medium. So the cell availability on the surface of hydrogel is no problem. The problem is in the center of the hydrogel. Even though the hydrogel is also a porous structure, there's not enough pores for the cells to live. And that's why we need the channels. And this is cell availability from the surface of the hydrogel all the way to the center of the hydrogel. For this sample with channel, we don't have the center 4 millimeter and 5 millimeters depths, because they are channel in that depths. But we can see the green one, green cells are more in the one with channels compared to in the one without channels. And then this is a showcase for what the 3D printer is capable of and what this technique is capable of. We can create different 3D printing structure and then 3D models, and then different type of shape of organs. And we can also create different type of channels as well. this is second topic, and now I'm gonna quickly go to the third topic. So the third topic is the upstate medical university, the medical professors, they reach out to me saying like, oh, we want some drug carriers that only have 1 to 5 microns, but we want to control the release rate of the drug within the particles. So first, their particle is nanosize. So they want to incorporate the nanosize drug into micro-size carriers, and they want to control the release rate of the drug within the lungs. So why 1 to 5 microns? Because they don't want to inject these drugs into human body. They want the human body, or patient to inhale the drug into the lung to treat lung disease. For example, acute respiratory distress syndrome, chronic obstructive pulmonary disease, COPD, ARDS, and pulmonary fibrosis. Pulmonary fibrosis is more common after COVID. So they want the patient to be non-invasive, to get the drugs non-invasively, so they can inhale. So in order to inhale, the diameter has to have a limitation, because if the particle is too small, the particle will be exhaled. If the particle is too large, the lung will recognize the particle as a exotic object and clear it using immune system to clear it. So only 1 to 5 micron can reach deep to the lung, And they want controllable release. So because usually when the drug goes into the lung, it's going to burst and then immediately release, usually release in 1 hour. But what if they want prolonged effect of the drug, right? So this is our setup. We used electrospray. The difference between electrospray and electrospinning is electrospinning produce fibers. Electrospray produce particles. If you lower the concentration of the polymeric solution, then the fibers will be broken into particles. So we also got a core shell, same thing. We got a core shell structure in the electrospray. And then in the core, we incorporate their drug. Their drug is a nanocarrier drug, TD nano drug. They call it TD nano drug. And then the PO again is water dissolvable. The PLA is not, if you remember. And we can also create some pores on the surface. How to create the pores on the surface? First one, you can use volatile solvent on the shell, or you can introduce humidity into the chamber when you do the electrospray or electrospinning. And then we create this kind of particles, and you can see the particle based on the scale bar is from 1 to 5 microns, 1 to 5 microns. And then we investigate the particle geometry and what kind of electrospinning or material properties can affect particle geometry. We want a round shape particle, right? We don't want broken particles. We don't want the donut-shaped particles. We don't want fibers. As you can see here, we have some fibers. When we increase the material concentration and when we decrease the material surface tension, it looks like the surface tension, solution concentration, and voltage of the electrospray all have effect on the particle circularity. And the next one, we also categorize the particle diameter. If the solution concentration is 1%, 2%, 3%, if the concentration has high surface tension, low surface tension, or if the electrospinning has different voltage, will it have effect on the particle size? So it looks like the particle diameter will be affected by the solution concentration and surface tension, but will not affected by the voltage. And then we also investigate this, those factors influence on the surface pores. because we want to know how big is the surface pores and how we can control the surface pores. Looks like surface tension and concentration affect the surface pores interactive. And we also test the degradation. If you remember, we still need the polymers to be degraded, right? If their core shell size, if they have surface pores, would it be easier to degrade, right? This is day 0, day 3, week 1, and week 3. As you can see, they're broken up, which means it's good. They're broken up. They're releasing the drugs in the core, right? And then these experiments are done by upstate medical universities. They tested if the particles is toxic to the lung cells. So this RAW264.7 cells and THP1 cells, they are both lung cells. And the black one is microparticle with nanoparticle carrier. The red one is microparticle only without nano drug carrier. So they both have almost 100% availability for the cells. They also test. They also want to test if the microparticle has effect on the hemolysis, which means if the cells will bleed. Which means and the result shows that they both have minimized hemolysis effect on the cells. And then we test the drug release. So the drug here they use is doxorubicin, DOX. So there's 4 groups. The first one is just DOX, no carrier, no nano drug carrier, no microparticles. The second one is the red one. They put the DOX drug directly into nanocarrier, but no microparticles. The third one is they put the DOX directly into the microparticles, but no nano drug carrier. No nano drug carrier. The blue one is they put the DOX in the nanocarrier, and then we put the nanocarrier in our microparticle. As you can see, the fastest release, of course, is going to be just the drug. And then the second one will be the drug with nanocarrier, within nanocarrier. The third one will be the drug within microparticle. And then the slowest to remove one will be the drug within nanocarrier, nanodrug carrier, and nanodrug carrier within microcarrier. Then they also tested the antibacterial activity. It shows that the control one, of course, bacterial is really high. And then these 3 groups with drug, bacterial, 0, almost 0. And then the one without bacteria, just the microparticles, without the drug, just the microparticles is also, bacteria is also high. They also investigate the enzyme activity. They replace the drug with enzyme. They want to see if the enzyme still, works. And then they put the free enzyme, just the enzyme, lysozyme. And then the enzyme in the nanodrug. The enzyme in the nanodrug in the microparticle. And then no enzyme, just the nanodrug. And then no enzyme, just the microparticle with nanoparticle. You can see the enzyme still works if there's enzyme. If there's no enzyme, of course, it doesn't work. And that's it. Any questions? Thank you.
Thank you, Dr. Zhou. There is a question on the chat here by Roshi on slide 17. Even after day 7, the morphology of the cell is not visible. They appear round. Why does this happen?
The morphology of cells, they're still round. Is that the question?
Yes.
Okay.
The morphology of the cell is not visible. They appear round. That's what it is.
Yes. So I think the fluorescence here is just for the cell nucleus, not the cell cytoplasm. So the nucleus is always round. But I think it's also a good question. So in the hydrogel, the cell attachment is poor because the cell has no geometry to be attached on. That's why if you incorporate the fibers or particles in the cells, in the hydrogel, the cell will try to attach on the fibers or particles to have some shape. But in the hydrogel, they're like in the water. It's just in 3D. So hydro means water, right? So most of the hydro is water. So they're kind of suspended. The attachment is pretty poor. That's why the cell viability in the hydro is also pretty poor. One of the reasons. Another reason is not enough perfusability in the hydro. Yeah. I don't know if that answers your question.
Thank you.
Thank you, Dr. Zhou, for that wonderful talk. Just
Thank you.
briefly, I mean, at the very outset, in terms of vascularization, have you taken a look at endothelialization of any endothelial cells into the tubes? And I think it's more of a material property, where in your case, it might be the PLA and PEO, which is being washed away at the end. So have you looked into the endothelial cell migration? B, have you tried with any other materials, whether the tubes can still be formed with your technique?
Yeah, good question. We tried different materials. We tried PCl, we tried PS, we tried PLGA. So all biocompatible materials. And to be honest, as an industrial engineer, I don't have enough resources to do all biomedical experiments to all those materials. But it looks like the cells are attaching to the microtubes and growing along it. The next step, I would say, is not my expertise. We should send this to biomedical engineer for them to develop the biomedical part.
Understood.
Yes.
Hi, Dr. So it was nice presentation. So I was interested,
you.
like you showed the microtubes, and when you put it inside like a gel and extrude it to your material and extrude to your 3D printers, it aligns and forms the tube, the vasculature, right? Vasculature mimicking structures. So uh, is this alignment? What do you think it's the cause? Is it due to any the shear stress or the shear thinning behavior of your material that is causing the tubes or the broken down tubes to align in the direction?
Yeah, definitely. I think that's one of the reason. Another factor, like I said, that can affect it is the microtube length and the microtube concentration in the hydrogel, and also the hydrogel material as well as the bioprinter resolution, right? I think that those all will affect. But another issue with this method is if the microtube concentration is too high, then you're gonna need high pressure to
Mhm.
extrude the hydrogel. If the pressure is high, the cells will be dying. Cells are too fragile.
Yeah.
Yeah.
And see, some of the microtubules you said are in the range of 600, 700 microns. Would that not create any aggregation problem or nozzle clogging and other issues related to larger particles?
The microtube, you mean microtube diameter or microtube length?
Length.
Oh, length. Here, we can control the microtube average microtube length by ultrasonic the microtube in the water or in other solution. So the longer the ultrasonic time, the smaller the microtube length, which means it will be broken down more. So we can control it.
Okay.
Yeah.
I think there's some questions in the chat, Dr. Srinath.
Oh, yes, yeah. Dr. Zhou, I think this next question is from Isai Tamal. We have one question. I am working on in bone on chip, how we can create vascularization in microfluidic chip to mimic the bone microenvironment.
Very good question. I think for the bone, the major material is hydroxyapatite. So you probably want to incorporate hydroxyapatite into the electrospinning solution, polymer solution, and then electrospin the tubes out, and then incorporate them into the microchip. The problem is how to fix the microtube in the microfluidic device, right? So here, what I did is I incorporate the microtube in the hydrogel, and then put the hydrogel in the microfluidic device, and then fix the hydrogel within the microfluidic device. So you can take that as a maybe idea, but feel free to explore more ideas. Good, very good idea. Thank you. I think for the vascularization of bones, there are many mature solutions, because bone is a tissue that require comparatively less cells. If you imagine in your bone, you don't have many cells. You just have the structure. Right? You don't have many vessels in the bone. You have vessels, but you don't have many vessels in the bone. And that's why also bone tissue engineering is really mature, because you don't have to deal a lot with vessels and cells. I don't know if that answers your question. Feel free to ask any questions. Thank you.
Any other questions for Dr. Zhou? Please feel free to unmute yourself and ask the question, or you can put it in the chat too. All right. It seems there are no other questions. Thank you, Dr. Zhou, for this presentation. I think that upcoming week we hope to have the next speaker from Shine, Dr. Yogendra.
Absolutely, Dr. Singh. Yes.
Looking forward to it.
I have one question. Can I ask?
Yes, Jyoti. Go ahead.
Yes.
Sir, wonderful presentation. I particularly liked your first study because it relates to my area of research as well. So, actually wanted to ask, since you used PLA and PEO, what particular properties of PLA are you harnessing in this particular application? And also, did you study whether the degradation products of your electrospin fibers, how they are affecting the neovascular tissue regeneration? What is the timeline? Have you studied that particular aspect?
Oh, good question. So the question is why I use PLA and how fast PLA degraded, right?
Yes, sir. Like how it is affecting, because once it degrades, it will release some degradation products will be there. Since you're using PLA and PEO combination, they will be having some reactions and they will release some degradation products, and that will affect the neovascular tissue that regenerates on the site. So have you studied that, like how the timeline of degradation and its impact on the neovascular tissue regeneration?
Yeah, good question. Yeah, but the reason I use PLA is it's one of the most commonly used compatible polymers, and its mechanical strength is pretty nice. It's pretty good. And in terms of the degradability, I think we don't have PEO in the cell culture. We dissolved the PEO before we put any cells because we want the tube structure instead of the fiber structure. So we dissolved the PEO. For the PLA, to be honest, I haven't tried any degradation studies because I know it's biocompatible with cells. It's not toxic to the cells. So we didn't try that. And for the PLA to be degraded, natural environment probably gonna take months. Yeah. So we didn't try that.
Okay, sir. Thank you so much.
Yeah, thank you. And the ultimate goal is for the cells to grow around the PLA tubes, and the cells will form the vessels by itself. Then whether PLA is there or degraded doesn't really matter.
Yes, sir. Did you understand, in how much time the new tissue formation occurs? Did you reach to that level where you studied, in how much time new tissue is forming
Yeah, really good question.
around?
So for this one, this red image, fluorescence image, is only 15 hours. Right? It's only 15 hours. It can form some perfusible structures. We have another paper talking about it. Is you put the fluorescent microparticles from one side of the microfluidic chips, and all the particles can pass through and exit from the right side of the microfluidic chips. That means this structure is perfusible, right? And you can see what's the path for the microparticles. That means after 15 hours, it's already formed some kind of formation. For If you're asking like really vessels, that's a really good question, and I haven't done it yet.
Okay, sir. Thank you so
Yeah,
much.
this is a
Really
very
exciting study.
okay. Thank you. This is a preliminary form of the vascular lumens. You can say the lumens. Yeah.
Okay, sir. Thank you.
Again, as an industrial engineer, I don't think I should focus too much on the biomedical applications. I should focus more on the manufacturing process and mechanisms.
Yes, sir.
Yeah, you cannot do everything by yourself.
Thank you, Dr. Zhou, for the lovely talk and the discussion as well. Dr. Srinath, I will upload or I'll rather update you on the next speaker within next couple of days with expertise. We're just finalizing on a few names and then we'll take it forward from there.
Okay. All right. And our next speaker from Binghamton University is Dr. Safa Al-Kaifi. I think we will also share some of those information about her research. I will also email you.
Sure, we'll do that. Yeah, thank you very much.
I also have added the link information about, in contacting Dr. Zhou. If you have any research interest and potential collaboration, we have included his contact information in the chat as well. And we are very eager to have potential collaboration with Shine as well. So thank you for this particular opportunity, and we are very happy to have more discussion about this. And thank you, Dr. Yogendra. Thank you, Dr. Arun Kumar, and thank you, Dr. Geeta, for your continued support, and we'll be in touch. So first of all, I would like to thank Dr. Yingge for this great presentation. And
thank you for the invitation.
This meeting is recorded, and I will also share the link for this video. So we have this on the Panopto. I will also host this on my website as well. So all this information will be passed on to the faculty at Shine as well. Thank you all for today, and thank you all for attending today. We'll see you also pretty soon with the next talk.
See you soon. Yeah. Thank you so much. It was nice meeting you.
Thank you so much for the opportunity.
Thank you, everyone.
Thank you, everyone. Bye.
Thank you.